Perfect.
Cool.
Let me start sharing the screen. So good afternoon, good morning to everyone. So I'm very glad to briefly present you today some results have been carried out in the Roma group on the experimental non-classicality in causal networks. So let me share the screen. Can you see it properly? Yes, I guess.
Yeah, we can see your screen properly, or at least I can. Yeah.
Perfect. So let me start briefly. The goal of my presentation is to focus on experimental non-classicality in causal networks, and the goal is to provide you a bit of an overview from the different concepts of experimental implementation. So before starting this part, I would like to briefly present to my research group. We have several activities. So we have the quantum lab based in Sapienza, University of Rome. We have different, let's say, facilities, the Quantum Information Lab, the Quantum Computing Lab, and the Quantum Technology Lab. But today I'm going to be much more focused on the foundation of quantum physics concept. Here you see a bit what is the underlying strategy of the group and the research. Our goal is to exploit quantum resources, and we would like to exploit quantum resources both for quantum information processing, but also to investigate the foundation of quantum mechanics. So we have an impact in different fields of applications, each one which is also our conceptual part. And we are approaching these challenges with different platforms, all based on photonics platform, but where you may have different technologies. Let me mention on photonics, on chip devices, fiber networks, standard bulk optics, and also some more specific devices, which are named, for instance, cuplate and chiplets, which allows you to manipulate more sophisticated degree of freedom of light. And all these activities are then developed to carry out different tasks. So this was a bit the perspective from the research group. But now let me jump on what is the goal of today's presentation. And the focus is on the concept of causality and the interplay between causality and quantum information. So this is an outline of my presentation, and I would like to introduce briefly the concept of causal structure, and then I would like to investigate non-locality in quantum systems, and then we would like to see how you can generalize this concept of non-locality to more complex quantum networks. This is where we will start addressing the concept of the interface between causality and quantum information. So, as first ingredient, I would like to make some very general introduction about the concept first of causal inference. So the concept of causal inference is to decide which causal models are compatible with observed data. So the key point of an experiment is that you have some observed data, which are your experimental outcomes, and you would like to see what can be the causal explanation behind the data you have acquired. We always have to be very careful about the difference between correlation and causation, and especially what we would like to see in this presentation is how quantum effect may lead to correlation which are not understandable when you use classical physics. So that's the general framework. Now we would like to work at the interface between the concept of causality and quantum mechanics. And in this framework, I would see two main research fields which have seen a growing interest in the last 2 years, both, I would say, addressed by several partners of the QISS consortium. The first research line, which has been mainly addressed by Taza Bruckner and also experimentally investigated by the group of Philip Bartner, is when you try to have indefinite causal structure. So where you have some dynamics where, since you have quantum processes, you are not in the condition where A influences B or B influences A, but you have more a superposition of A influencing B and B influencing A. And this was this research line started in 2014, and which have several experimental implementation, and where key ingredients was the concept of quantum switch. Instead, my talk will focus on a different research framework, which is how you can address non-classicality in causal framework. So you really would like to take the causality framework, define precisely what is a causality framework, and thanks to this approach, identify where you see a signature between on having classical resources or quantum resources. So again, this you see some of the paper. You have been you have several contributions in this framework. Mainly we see by the group of perimeter by Robert Speckens. You had some experiment. You have the theory developed by Rafael Chavez and other groups. And so today I will focus on what have been our activity within this framework of non-classicality within this scenario. So now I would like to start defining some element. I will explore it in my presentation. And the first ingredient is to introduce the concept of directed acyclic graph, DAGs. So this is a framework which is adopted in the classical inference framework, where you would like to investigate the causal relation between different variables. And then you can introduce the following diagrammatic approach. First, we introduce the nodes, and the nodes correspond to variables. Then you introduce the concept of arrow, and arrow means that you have a causal connection between variables. For instance, you have this xe, xj, and this means you have a causal influence from xe to xj. Then you can put these ingredients together, and you can get what are named directed acyclic graph that I will name during my presentation DAG. And the DAG allows you to represent what are the causal connection within a given scenario. For instance, we have the following one on the left side, where you see different variables, and the different arrow tells you who is influencing which other variables. So when you take this picture represents the causal connection at a given moment of time where all the variables are in the given fixed position. So in the following graph, for instance, if you take the variable x3, you will see that the variable x3 is influenced by x4, lambda 3, lambda 1, and zeta. And these four variables are named the parent of the variable x3 because they are the variables which are directly influencing x3. And for instance, you may see again that lambda 3 in this graph is the parent of x2 and x3. So all you have this DAG, you can write then any, you can represent also probability associated with the different variables via Markov condition, because each variable x3 is E will be influenced by its parents and so on. And this is what at the end leads you to the acyclicity. You cannot have a system, since you are working at a given time, where x3 is influencing x4, x1, x2, and again x3. This means you cannot close the cyclic graph, because this, I repeat, tells you what are the connections at a given time. So for instance, you may have now this other example where you see x1 is influencing x2 is influencing x3. And this tells you that at the end, x3 is only influenced by x2. And then obviously x2 is influenced by x1. So that's a general framework. But then our idea is now to approach the correlation in a general scenario using these formats. So what we can do, we can start with some simple network. So let's consider the following network, which is named the instrumental scenario. I will comment this later on, where you may have X, which is influencing A, which is influencing B, and a question can be, does A and B are influenced by a common latent factor? And that's the case of some clinical trials. So you may imagine, I have a medication, I have a treatment, I have a recovery. Are my data compatible with this causal connection, or can there be any latent factor which is influencing both the treatment and the recovery? So the key idea is that once you have a DAG structure, the DAG structure will lead to some causal constraint on the observable statistics. So this was a way to introduce the topics, and now we can go to the following step, which is how we can use this causality framework within now the test of quantum mechanics. So the typical approach will be the following. When we run an experiment, we have some statistical data. We will have some statistical data, and once you have the statistical data, the question can be, are these data that I got compatible with some assumed causal structure? And this will exploit that when you have a causal structure, you get some inequality. And then if your data are not compatible with this inequality, you can exclude the causal structure. So it's more an approach by exclusion, that your data are not compatible with something else. And now something, and I will provide you some clear example now with the Bain inequality. You can use this approach to certify non-classicality, because you may say the following: I have a statistical data. I know that I have a given causal structure. I find that the statistical data are violating the causal structure, but since I know that the causal structure was the right one, I must conclude that there were some non-classicality in the physical systems. So one can use the violation of causal structure as a way to certify the quantumness of some of your resources. So in order to make this scenario clear, I will use Bain inequality, and then eventually we'll come back to this slide. So what we can do now, a starting point, is to consider the Bell scenario. So it's a standard Bell test. And let's try to address the Bell test by looking at it as a causal DAG graph. So when you have a Bell test, you have Alice and Bob, here A and B. Alice and Bob share a common resources, which is lambda, which can be the local eigenvariable models. And in the Bell test, Alice and Bob decide which measurements to perform. And so a Bell test can be represented by the following DAG scenario, which is represented on the left. You have X and Y the measurement input, A and B, what are the outcome of the measurement, and lambda is a latent variable, which is a resource which is shared between Alice and Bob. Once you have this Bell scenario, you can derive, using this DAG, a local causality constraint. And this local causality constraint that to derive is fully equivalent to a closer order Shimon-Inhofe inequality. It's a Bell inequality. So what you are deriving simply is a Bell inequality starting from the DAG, which represents your causal scenario. You derive inequality. And once you have derived this inequality, if you violate this inequality, you can say, look, these are my statistical data. I was indeed implementing this DAG, but since my data are incompatible with my inequality, I must conclude that there is some non-classical resources which was somehow providing a correlation between A and B. So what you do here, you use this direct acyclic graph as a way to certify the quantumness of your resources. This is what you can do when you have a Bell scenario. What you can also do, you can use the same approach in different frameworks. For instance, you can use the same approach if you have in mind what is named a so-called prepare and measure scenario, where you have you prepare a state which is transmitted from Alice to Bob. Alice prepare with the observable X, the preparation. Bob measure according to the observable Y. Lambda is the state which is prepared. D is the outcome of your measurement. And then at the end, what is this? It's what we name a prepare and measure scenario. You can use it. And if you take the prepare and measure scenario and add a dimensionality assumption on your systems, you get what is a dimension witness. So that's a different way to consider what is a dimension witness. You assume a DAG scenario, you add on top of that a dimensionality assumption, and this gives you some inequality. If you violate this inequality, you will get a witness of non-classicality of quantum systems. So again, I'm a bit repeating myself, but I would like to focus on this key point, that here you are combining statistical data, assuming causal structure, plus violation, as a way to certify the quantumness of your results. But what is the interesting part is that we know very well the Bell scenario, but now by correlating the Bell scenario with this DAG framework, we may have a tool to generalize the Bell approach to identify correlation, quantum correlation in any classical framework scenario. And this is what I would like now to discuss. So the goal is now to extend the previous paradigm and to analyze different frameworks. So I recognize that this paper I'm mentioning has been carried out in collaboration with my group, especially Emanuele Polino and Davide Poderini. That's in collaboration with Rafael Chavez in Nadal, and also several of these papers also in collaboration with the Perimeter Institute, in particular with Robert Speckens and Danny Wolf. So we have this other paper, which is published a couple of years ago, and this is the following. You see on the top right the well-known Bell scenario. But what happens in the Bell scenario when we break slightly the Bell scenario? For instance, if there is no more choice in the no more freedom in the choice of the Bell measurement. What happens if we have some correlation on how Alice and Bob are choosing the settings they are measuring? And so each of these scenarios where you break the initial Bell test is represented by different DAG. So each time you break one assumption of the initial Bell test, you are adding some new arrow, as you can see here. And then you can, for this new DAG, derive new inequality. So you have now a very formal way to investigate what is the impact of measurement and dependence, the figure 2, and then you can investigate all this scenario. I'm not focusing more on this paper, but this gives an intuition. You have now a formal way to really generalize what happens when you add any sort of correlation in your experiments. I would like now to go to a following step, which was the following idea. A question which was raised initially by Rafael Chavez is, what is the simplest causal scenario in which we can prove that we have a quantum resources behind? So we know very well Bell test. In Bell test, you violate the Bell inequalities when you have entanglement. But can we find something simpler than a Bell test where you see an impact of quantum resources? And one may say, okay, what is the simplest causal inference problem? The following one, where you don't know if A is directly having an influence on B, which is on the right side, or whether A and B has a common latent factor, lambda, which is influencing both A and B. So these two scenarios that you see, you cannot disregard one with respect to the other one. So because these two causal models lead exactly to the same measuring distribution. You need to go for something more sophisticated. And something more sophisticated is the so-called instrumental scenario, which was proposed by Judy Perl in '95. I mean, it was investigated a bit more. And that's the instrumental scenario. It's something in which, I've shown it before, you have A, which is influencing B, X can influence A, and your question is, does A and B are influenced by a latent factor lambda, which is somehow correlating A and B by another effect, which is not the direct cause. So what can you test here? And then the question was also, with this scenario, having lambda classical or quantum, do you obtain some departure? as you are in the Bell test, because that will be a scenario which is simpler than the Bell test, where you have a bipartite system. So this is what we investigated theoretically and experimentally in 2018. So one takes this scenario, this incremental scenario, one imposes classical Markov condition, and one obtains an inequality. So you say, okay, once I got this inequality, can I violate this inequality if lambda is quantum and non-classical? And this is possible. You can see a violation if you take x to be a trichotomic variable, which take value 0, 1, and 2. You keep A and B dichotomic, and you may have a lambda factor. And once you have this, you may get a Bell-like inequality, which is written here and which is bounded by 3. So now you have an inequality which also repeats for x, which is trichotomic, A dichotomic, and B dichotomic. And so you may ask yourself, if I have a quantum, if lambda is quantum, so if my correlation between A and B has a quantum correlation, can I beat the classical value? And so answer was yes, you can get 3.82. So this is very similar to a Bell test. When you have a Bell test, let me go back to the slide. I want only to that this point is very clear. You have the following scenario. You got a 2, and if you have a classical correlation, and you get 2.82 if you have a quantum resources. Now in the instrumental scenario, you have the same path. You get 3 as bound, and if you have a quantum resources, you get 3.82. And in that case, you can break 3, as you may see. So this is the idea, but you see now that this instrumental scenario is quite different between Bell test, because now in this scenario, A can influence B. So you see the structure is pretty different. It's not a bipartite system, it's a monopartite system. So what we did, we implemented this experiment, and it turns out that we did it with photons. So you see the 2 photons, which represent A and B. Lambda is an entangled photon pairs. So you have entanglement. You have to find obviously the right observable, and you need to have now a feed-forward. So you want Alice to influence B, because this can be done. And you need to have Alice influencing B if you want to break the classical bound. So the first experiment we did, you see, we are able to go above 3 by getting 3.26. And then we had other paper in which we further improved these results. So to make a story long, this long story short, we have shown you that we have another framework, another causal scenario, where you see a departure between quantum and classical, with a very close approach to what was done by the Bell test. But thanks to this DAG formalism, you are able to extend it to other scenarios. So, something else that we have been doing, and I will be also short on that, is the following. There is another approach that you may use to investigate if you have a causal influence. Until now, what I've shown you was a model where you had a causal DAG and you got an inequality, and if you violate the inequality, you get a quantum signature. But we have another approach that we investigated also very recently, which is where you have an intervention. What is an intervention in the causal inference framework? It's a process in which you intervene on a variable, on A. This means you force A to take a value. That's an intervention. You have a way to say A takes this value. So you remove all the arrows which are influencing A, because you are putting the end in the apparatus and you are forcing this variable to take a given value. And then once you force A to take a value, you may ask yourself, now that I have imposed A to take a value, how much I am influencing B? So, and you have a way to quantify this by this quantity, the A's, which is the average causal effect. So average causal effect from A to B tells you when you change, when you force A to take different value, how much B is changing. So it's the maximum change. It's the probability of B depending of B by changing your intervention. And you may ask whether you can use this intervention to highlight, to identify quantum correlations. And to do this experiment, what we did, we again used the instrumental scenario I showed you before, which is one shown here, where it's the same experiment of before with a better apparatus, where you have an entangled photon pairs, where you have Alice and Bob, and what we see here is your scheme. Now, what you would like to do, you first would like to carry out an experiment without interventions, which is the same experiment I've showed you before. And then what you do as following step, you do an intervention on A. This means you force A to take a value. This means you are imposing the value. You are not even measuring the photon. Say, look, the outcome of my measurement was +1 because it's my intervention. And then you observe by imposing this value how much you are affecting B. And then you can investigate whether you may have a departure between the average causal effect if you have a quantum correlation between A and B, and this is what we observe. And moreover, what we could observe is that by this approach, you can observe quantum violation even in a scenario where you could not observe violation of an inequality. So this intervention allows you to address some correlation otherwise not accessible. Only one slide to mention, once you have a way to characterize your quantumness, you can also exploit it to carry out randomness generation and certification. This is what we did in this article, but I'm not focusing on that. So what can be the following step? I hope I give you some intuitions that by this DAG approach, you can address more complex scenario. We have seen the best scenario with a single source, but now what you can say, okay, we worked until now in simple scenario, but we can now start going to much more complex scenario on the right side, and you may try to use this different scenario, derive the DAG, derive the inequality, find the boundary, and then if you have a boundary, you have a way to certify your quantumness. And this is what we have been working a lot in the last time, where we have addressed non-locality of complex quantum networks, where we addressed networks with a variety of geometry. And the motivations are foundational because you really would like to see how much departures there in between this classical and quantum correlation, but then that's also a way to certify that indeed your underlying resources are truly quantum. And on that, I would like to show you some perspective of some scenarios that we have investigated. Matt, may I ask you, how much time do I have left, more or less? Because I can adapt my presentation to the available time.
Sorry, did you ask the question there?
Yeah, how much time do you think I have left, more or less?
How much would you like?
Okay, maybe I can. Is it fine if I do 40 minutes, 35?
Yeah, I think 35 to 40 is fine. Yeah.
Okay, thanks.
Yeah, good. Thanks.
Thanks. So what we had here so now is to have something where, as I told you, we have some more sophisticated scenario, starting from a bilocal one, where you see we have now 3 nodes, A, B, C, but what we assume is to have 2 different models of local eigenvariable. So the idea is to say, this was first investigated by Stefano Pironi and Nicolas Gissin, Cyril Branchard, and Denis Rosset, where they investigated this bilocal eigenvariable model, where you have now 2 sources of entangled photon pairs, and you different sources. So I'm not going down into the details, I can use this for question eventually later, but the key part is that you have now a non-convex set of correlation. So when you start having several sources of eigenvariables models, this sort of inequality becomes much more tricky. And you get this concept of bilocality. I don't want to go too much into that, but to show that we implemented several experiments on that, where we implemented the first bilocal inequality, and also several other groups had some follow-up activity on this research. We'd like to mention also the group by Jeff Pride, which implemented this. There was a complete experiment done by John Repan in 2019. And then we started also addressing more sophisticated scenario. For instance, the one here on the right side, where you have this star-shaped quantum network. So where you have different sources, and your observable are organizing according to a star geometry. So on that, we implemented several experiments, also connecting different buildings in our campus and so on, in order to have a growing complexity of the experiment. So in that case, you really have different event sources, technology, and nodes. Also, I mentioned you can also have this correlation now, which are in a star-shaped configuration. So again, you are changing more and more the geometry of your device, and this allows you to see new sort of correlation. So I would like now to, I'm close to the end, I would like to comment another structure which has attracted a very growing interest in the last time, where you have a triangle structure, where you have three nodes, and then the three nodes we are connected by different sources, lambda 1, lambda 2, lambda 3. And there was a strong effort to ask in this triangle network, sorry. This means my time is over because my voice is going, so that's a confirmation that I must converge. Well, this triangle network is interesting because it has some very peculiar correlation. So what we did again, we investigated this triangle scenario, and we carried out two experiments. These were in collaboration with again Perimeter, Nadal, Chavez, and my group in Rome. Well, first we had this scenario which is triangle and different inputs. And we investigated when we had the local structure of quantum non-genuine violation and so on. And you see there is a variety of inequality that you can derive. But you start adding really non-trivial result as output. And then what we did, we started having a triangle network with external input. I'm making a long story short, but we really could certify that our data were incompatible with a scenario where only two pairs were entangled. So again, you may have several tests which provide you a stronger and stronger support that what we need you're observing is a genuine correlation between the three sources in the triangle. So these are a kind of hierarchy test, more and more elaborated, and the higher you go, more confidence you have that you're right. Then I would like to go to our very last results, which was the idea, which was created to see whether you can have what is named a triangle without external input, which is a scheme B in the center, which is a peculiar scenario because the idea is that you have no input from outside. It's a scenario where the structure, you are not pushing any button. It's a causal structure itself, which is providing the input to the measurement. So you see in A of the best scenario, in B, it's the system itself which is driving the experiment. And then it's now a kind of co-op scenario where you don't need to have the freedom of choice. Because typically in a bad test, you need the freedom of choice because you need to pass to decide what observable you need to measure. But now you get a structure where it's the experiment itself which is driving all the measurement setting. And so what we carried out, this paper is of last year, which is experimental non-classicality in the causal network without assuming freedom of choice. Where you are assuming no freedom of choice, you don't need, because you don't need to provide any input externally. And this is how we implemented it. Then we can comment this a bit more later. What you get of this experiment, which indeed was using classical and quantum correlation in order to get the violation. And now this experiment was interesting because on one side that to carry out the framework, the concept, but also we needed to develop some technique to check that indeed what we were observing was going as expected. And then this required to combine a technique of machine learning, deep learning, and so on in order to get the right non-classicality detection. And so at the end, what you have is that you are able to witness a non-classicality using a data analysis technique, which assumes only the causal structure of the triangle scenario, and you don't require at all any assumption on the freedom of choice. Well, so this for me is an example of now by really merging this approach on causal structure with quantum resources, you may disclose new scenario of interest. So I'm close to the conclusion. So I would like to summarize. I provided a perspective on how you can use causality framework as a tool to detect non-classicality and as a tool to identify new resources. And you can go beyond the violation of inequalities. I've shown how you can see experimental violation of classical constraint on different causal effect. I've shown how you can implement more complex networks. Something which I've not discussed, but which has been exploited in several results, is how one can use machine learning as a tool for characterizing non-local correlation. And this in particular was necessary for the last experiment, because then you could not exploit any inequality, and then you need to use more advanced tools in order to at the end validate your experiment. So thank you very much for your attention. So it's 37 minutes despite my voice. Thank you so much.
Great. Thanks very much, Fabio, for the really interesting talk. Okay, that was great. So I'll keep an eye out now. Please raise your hands, everyone, if you have any questions. And yes, we do. I believe we have a question from Richard.
Hi, just want to say thanks for the excellent talk. Just a comment on some of the stuff said at the end regarding using machine learning to spot quantum correlations. I was interested if you consider things going the other way. So you have some systematic way of describing how these correlations are coming about. Could you use them to investigate the expressivity of models that you build on top of them? So you have one particular DAG that describes a particular causal structure, and you say, okay, well, if I have some sort of parameterized structure on top of this, or in this, then I'm able to express these things. If I was to have a slightly more complicated or different structure, then I'd be able to express something else. Is that something you've considered since you've been thinking about machine learning and these quantum, these networks in this way?
That's a very good question. That's something that we have not considered. So what we did a couple of papers where mainly the goal was to train the system in order to find a way to certify whether your resource was entangled or not. That's what we did. So for example, in this case, what we had to do is that the theoretical paper was saying, look, there is a strict distribution, which is a way to certify this triangle. And you measure the distribution. And at the end, your distribution will never be the theoretical one, because it will be always experimental. And then the goal is, okay, what can I say about my data, which are not precise distribution, how we can then infer whether our data are still compatible with this expected scheme. So that's what we did here. And so, because we had no inequality to test, So that, but that's not what you are asking me. Your question is very good, and because it's something which it's the right direction to try to generalize the tools. Where so typically these tools, the main inequality is something very specific. Say, okay, I have my test, I want to test this inequality. No, you would like to have something more general tool where I'm not giving exactly the column sort of models to be tested eventually, but you would like to disregard the family of that and how eventually machine learning could help us in this framework. So that's something to be discussed again, but it's not something on which I've been working yet.
Okay, thanks.
Okay, since I don't see any other questions right now, I have a question I'd like to ask. So in the first, okay, it's two bits. I think in the first experimental setup you showed that was from your lab, you had, it was the first time you mentioned some kind of photonic sources. Do you have this slide?
Let me go.
Yes.
Something on it.
Yes. Well, so my question was going to be while you're looking for it, I couldn't really see where X was in this first picture.
Okay, so X was in this case was a measurement setting where you have three possible sets. So X was which basis you want to measure, and it could take three different values. So in the best test, it takes two values. It's here, X was what is your observable. And that, okay, it is here, it's on the other side. So you see on the corner left down, you see the three observable which Alice is measuring. So X is 1 to 3, and depending whether it's 1 to 3, you measure sigma X plus sigma Z, sigma X or sigma Z. I hope that was that addressed your question.
Yeah, it does. And so this is a really naive question from a theorist. Why do you use some kind of photonic setup? Is it because like that is what your lab is about, or is there like some particular reason to do things this way? Or
I will say both. First, we have photonics out. Then the second one is that in this scheme, what you would like to do is that you would like to have the second measurement, which is done after you have done the first one. So if you see the setup, you see that we measure one photon. The second photon is going in a fiber delay, so that you delay the photon, and you measure the second photon after you have received the information from Alice, which is the opposite of the bad test. So in the bad test, you want something which is space-like separated. Here you want one photon to influence the measurement on the other one. So photonics is also a good platform to have this space-like, this feed-forward scheme, where you delay one photon, you have a very quick detection, and you change the state of the measurement setting on the second photon depending on the first one.
I see. So that's this big coil of wire in the middle then.
Exactly. That's the feed forward. So that was on one apparatus, and you can see also on this one. You see the fiber in the center, no? So the picture of the pool with the fibers there, which is the fiber delays.
Okay. Okay, good. Thank you. See, so there any other questions in the chat? If you have any questions, feel free to raise your arm or just pipe up. Let's see. Okay, since there isn't right now, I do have one more actually. It was right near the start, you mentioned something about dimensionality witnesses.
Yes, let me go.
Yes. So maybe my question is just I didn't quite understand why you need to assume some kind of dimensionality condition to get, I think it was like a violation or a witness here, or what the dimensionality means if you don't know what the systems are made of yet. Like if you don't know the system is classical or quantum, like it wasn't clear to me like what dimensionality meant, like what that number described.
So thank you. So the dimensionality witness were a bit popular, we say something like maybe 10 years ago, more or less.
Okay.
Well, but this were presented in a completely different framework. The idea is more way, okay, how can I certify that my system has some dimension, which is larger than some value, no? And then they divide all these witnesses of dimensionality. And then here we wanted to show that you can connect this dimensionality witness with this DAG scheme. And at the end, you can see that having this DAG constraint, this PAM, which is paper measure constraint, plus a dimensionality, this is what directly leads to the dimensional witness. So again, it's still the case always the following. I have some constraint on my interrelation. In this case, I need to add something else, which is, okay, let me see if lambda has a given dimensionality, which fixed, so lambda can take up to some values. This will lead me to some dimensional, to some boundary. I hope I clarified.
Yeah, I think so.
But the idea is always to say, okay, there is a kind of ingredients, the causality framework, that you can expand different framework, and this allows to also merge approaches which are typically addressed independently.
I see. And so we've seen lots of talks and lots of interesting work about like experimental tests of say like near-term tabletop experiments for testing, say, the quantum nature of gravity, things like this. And you mentioned at some point that the nice thing about drawing all these bigger, fancier causal structures is there are all sorts of new quantum resources you can identify and verify are in your structure. Are you moving anywhere towards those kinds of problems, or does this have anything to do with these kinds of problems?
So that's again a very good question. I guess that's a natural evolution to be addressed eventually within the QISS. So until now, our goal was really more to identify correlation in the photonic systems. But once you have this more general framework, one may ask, can we apply this tool to maybe identify some experiment which is easier to be addressed with a system with mass, where maybe it's easier to see that you have some kind of quantum correlation? That's a very good point. So a possibility that we discussed will be where one can exploit the instrumental scenarios that we see here now as an equivalent to what was a Varlet-Vedral approach, where in that case I wanted to see entanglement in a more standard balanced scenario. Can we use the instrumental scenario maybe as an approach to test some kind of quantum correlations? Maybe something which is easier to be tested, but it's not something which is still very preliminary.
I see. So maybe we'll just give people a second to raise their hands if there are any more questions. Let's see. I don't see anything popping up. No. Okay, cool. So in that case, yeah, I'd like to say thanks very much for a really nice talk, Fabio. That was really interesting. And if we can take a chance to thank Fabio. Thank you very much.
Thank you so much. Thank you, Richard. Bye-bye to everyone. Bye-bye.